Welcome everybody to What's New in Visual Studio, 64-bit IDE, C++ 20, WSL2, and more. My name is Cy Brand. I'm the team's C++ developer advocate, and we will be answering questions mostly in chat today. We will be pushing right to the end of our allotted time slot. So please ask your questions in chat and in the Q&A section. Marian.
Hi, I'm Marian Luparu. I'm the group product manager for the C++ team. And we're both excited that you chose to spend the time with us today. Thank you for tuning in, whether you're in person, tuning in remotely, or you're going to watch this recording after that. Before we jump in today's topic, I'll say that we got a lot of going on this week at CppCon. So if you have any questions about any of the announcements today or throughout the week, questions about Microsoft products and in general, you just want to talk about C++, come by the Visual Studio channel on Discord and chat with us too, or the rest of the Microsoft folks attending the conference this year. As with every year, we have a survey that will help us learn more about what you do, and it may help us build better tools or services for the future. So please head over to aka.ms/CppCon and take a few minutes to write down your thoughts. And do share your feedback on the survey, whether you are a Microsoft customer or not, because we're interested in learning from everyone that writes C++. It's in our mission to empower every C++ developer and their teams to achieve more, whether you're using our tools or not. And that's a hefty goal. Sometimes that's something that we aspire to, and is also something that we work towards day after day. And there are 5 main ways that we do that. First, is by participating in shaping the C++ standards. This goes beyond attending standards body meetings and writing proposals that we believe our C++ customers would benefit from. Our team also makes an effort to validate designs and create experimental implementations for proposals to provide the feedback and give confidence to the standards body whether the proposals are on the right track. Then it is the work we do on our tooling by investing in the MSVC compiler tools and libraries, by simplifying the acquisition of everything C++ through Vcpkg, and by innovating and enhancing our C++ experience in Visual Studio and in Visual Studio Code. Today, we will be focusing on the middle 3, which is MSVC, Vcpkg, and Visual Studio. But if you would like to hear more about Visual Studio Code, Julia will have a session tomorrow where she will be sharing more about our free open source multi-platform code editor and what you should be expecting in terms of C++ development experience when using it. She'll also have some very cool demos, so please tune in tomorrow at her talk. Switching now to the main focus of our talk, Visual Studio. It may feel like yesterday, or it may feel like a decade ago. Mileage may vary. And by the way, I hope you're staying safe out there. But it was last September when we were all still adjusting our home monitors and tuning in remotely to our first virtual CppCon. There, Cy and I presented a case for how Visual Studio, with the work we've done in the recent years, is super ready, prepared to enter a new decade of C++ development. Our work on C++ 17 and C++ 20 conformance, investments in simplifying development for cross-platform code bases, and open sourcing STL are primary examples of that. And we committed there to continue to focus on what we believe are the right challenges, the right big problems that you need Visual Studio's help with in the next decade. We're here 1 year later to report that we've been hard at work to have this decade off to a good start. Through several major updates, Visual Studio 2019 has expanded its functionality to reach 16.11 version, which in August this year became our final version and our long-term servicing release for Visual Studio 2019. In parallel, earlier this year, we released the first preview of Visual Studio 2022. If you haven't kept up with the news of each of the previews, no worries, you are here now, and we'll catch you up on everything you need to know. But if you did tune in to our previous announcements, you may already know that Visual Studio IDE moving to 64-bit. was one of the big initial announcements. Some may argue it's overdue, maybe it is, but we do believe that this change puts Visual Studio in a great position to scale to the needs of this new decade of C++ development. And it all starts with an invitation to all of you. On November 8th, Visual Studio 2022 will be generally available, and you are invited to the launch event. Mark your calendars and follow the link for more details. We'll look forward to seeing as many of you there. Now, with this new release looming on the horizon, let's get something off our chest right away. Upgrading your code base hasn't always been easy. So let's talk briefly about how we can mitigate this and have a smooth upgrade experience to Visual Studio 2022. You may know from previous releases too that Visual Studio goes to extreme lengths to make sure that any customer can easily migrate their code base. We continue making this a priority for the product, helping at every step of the way. So step one, of course, is to install the latest Visual Studio. But when you do that, as you're used with previous releases, Visual Studio 2022 will be side by side, so that you can easily move between the versions as you please. So you can try Visual Studio 2022 while still spending most of your time maybe in the older version that you're proficient using. And if you want to start the upgrade process cautiously, you can install inside the Visual Studio 2022 the exact MSVC toolset that you use today in your previous IDE. And no project upgrade would be needed. You get to try the latest IDE improvements risk-free, and IDE would be building your sources in the same way the previous IDE does. And of course, once you feel comfortable trying out the latest enhancements in the toolset as well, you only need to upgrade your projects to the latest compiler without having to worry about third-party dependencies or even first-party dependencies other teams that your company provide. Binary compatibility guarantees that regardless of how much control you have or really don't have over your dependencies, you can still use the latest VS with the latest MSVC toolset on your own source code. And last step is to compile your dependencies too with the latest compiler. After all, you do want the benefit from any perf improvements that you get for free from recompilation. Of course, not everyone has access to the source code of their dependencies, so your experience here would vary greatly. But even if you do have access to the source code, it may not be a trivial activity because it's not your code base. But luckily, for all of your OSS dependencies, you can use Vcpkg to easily recompile them using the latest MSVC compiler versions as well. Optionally, once you are on the 2022 train, if the rhythm of upgrades for Visual Studio does not match the rhythm or comfort level that you have, you can lock your code base on a specific minor version of the compiler while still staying current on the latest version of the IDE. For more details regarding any of these, check out our porting guide and the link down there. And I hope this gives you peace of mind that everything you see today for the rest of the talk is within reach, even for a maybe more complicated code base. All right, so moving to our main agenda today, we'll cover the latest work on standards conformance with C++20 being a massive update with lots of work being done there. Next, we'll talk about code safety, where we'll discuss the tools you need to make your code more secure. Then we'll dive into cross-platform development, and Visual Studio is an IDE that lets you target not just Windows, a lot more than that, and we'll demo that today. And finally, we'll wrap things up with productivity, all the things we've been working on to make your dev life easier, both as an individual and as a team. So let's start with conformance. And last year here at CppCon, we were announcing modules and coroutines as feature complete and committing on a course to complete C++20 features and officially introduce the stood C++20 switch in the MSVC compiler. Our first big announcement for this year is that as of version 16.10, C++20 is now feature complete in Visual Studio. All features are fully implemented, and you can give them a try today. We've also introduced in 16.11 the new STD C++20 switch, which means that all of the features available under that switch are now production ready, with all of the guarantees that come with that. And that's not all, because STD C++20 is binary compatible with older C++ standards and even older compiler versions. This means you can adopt C++20 in your production code today. Imagine having access to modules, coroutines, concepts, and more, and being able to gradually modernize your code base this way, while other binary isolated areas of your program don't need to necessarily move at the same speed as you do. Now, subset of C++20 features are still available under the STD latest switch only. We're actively working with the standards body to resolve the open defects in C++20 for format ranges and parts of Chronos that will allow MSVC to provide binary stability for these features as well. And once that happens, we will integrate those two under the STD C++20 switch. Now, this together with the fact that GCC and Clang are also making solid progress on C++20 as well, we know that more and more of you will have the option soon to move to C++20, which brings me to my next point. As more of us get serious with C++20, rather than just toying around to learn with a language, we start adopting in our real code bases, and we need an IDE that comes with code assistance, with code navigation, and debugging for all of this new C++20 constructs. It just so happens that in addition to the work we've been doing in the MSVC compiler and libraries, we've also been super hard at work towards building a state-of-the-art support for C++20 inside Visual Studio. Visual Studio will provide you with full end-to-end support for C++20, irrespective of the compiler or platform you're targeting. And by end-to-end, I mean support for editing, for building, and for debugging C++20 code. In the editor, you have code navigation, inline linting, colorization, formatting that you learn to expect from Visual Studio. They all have been updated to support the new C++20 features. IntelliSense has been enhanced to support the new language features as well. For example, concepts, as you can see from the screenshot at the bottom, IntelliSense can provide member list information inferred from a concept definition. We've also vastly improved IntelliSense to handle the high demands of ranges. And we're actively working on right now on putting the finishing touches to the design time experience for C++ modules. At build time, if you're using MSVC and MS-Build, you're ready for C++20. And if you're using CMake, GCC, and or Clang LLVM, many of the C++20 features are already there, ready to be used. Specifically for CMake, Kitor is actively working on supporting modules in CMake. And in parallel, we're also working on making sure that the module experience in CMake just lights up in Visual Studio in a similar way on how the MS-Build support in Visual Studio lights up today. Now, let's talk about the Visual Studio debugger. A piece of Visual Studio that receives a lot of love, but in there, no other feature has a more fundamental impact to the debugger experience than coroutines. Visual Studio comes with updated experiences for stepping, parallel stack, debugging visualizations, just my code debugging, that make the underlying mechanism for coroutines feel like magic, letting you focus on debugging your particular coroutine logic. I'm really excited about all of this. I could spend a lot of time talking about it, but I bet that you want to see this in action. So I'll turn it to Sai, who will give us a demo of the Visual Studio C++20 experience.
Okay, so I'm going to show the 4 main features of C++20 all working together. That's concepts, coroutines, modules, and ranges. So I'm going to create a new MS build application called CppCon, and I'm going to make a random number generation example. So it's going to look something like this. We're going to take an infinite stream of random numbers, and we're going to get this from something I'll call CppCon XOR shift. Now, XOR shift is a random number generation algorithm. I've picked it today because I can implement it in about 5 lines of code, and it actually generates pretty decent random numbers. Of course, I need to seed it with some high-quality seed, such as 4. Then I could take all my random numbers, and just print them out with a new line at the end. Right. Okay. So let's think about how we want to implement this. I want to show modules, so I'm going to implement this using modules. Now, if I want to use modules, I need to go to my project properties, to general, and switch C++14. I'm going to use C++ latest. Okay. Now I can go and add a new module. New module, this will create a C++ module interface unit with the extension IXX, and I'll call it XOR shift. All right, this gives us a few things. It says module XOR shift. That means that everything from here below belongs to the module XOR shift, and also we're going to export it and make it available to external code. Then we have a single function called myfunc, which is also exported. If we got rid of this, external code could not see this function. This is one of the benefits of modules. We can hide our implementation details so that they don't leak into contexts where we don't want them. But we don't want this function at all. We wanted namespace CppCon. And if we want to export everything in here, we can just write export namespace. Okay, let's implement our XOR shift function. So, like I said, I want this to be an infinite stream of random numbers. I don't have infinite memory in my machine, so we're going to have to generate these on the fly somehow. But to start with, let's implement this function as a single step in the algorithm, like taking in the seed or the current state of the generator and returning the next value. So we're going to return a uint64t. Our function is called XOR shift. We're going to take uint64t as an argument. Okay, so we immediately get squiggles. We could ask it to just add the header for us, but I just want to show you something quickly first. So it is in the cstudent header, but if we stick it here, remember when I said module XOR shift means from here below everything belongs to this module? Well, hash include just means to take everything from one file and dump it in here. So we're saying that everything in here is going to get module linkage, which is not correct. We don't want this. We want to take this and put it up here in what's called the global module fragment, just something to be aware of. If this was a regular import some module, absolutely fine. Modules are intended to handle that, but for hash includes, stick them up here. Okay, so that lit up IntelliSense, and now we can implement our algorithm. Like I said, it's fairly simple, about 5 lines of code. It's a little bit weird though. We take our seed, we XOR it with itself shifted to the left by 13, the very definition of a magic number. Then we do the same but shift right by 7, and then the same again but shift left by 17, and then return the seed. That is our algorithm. Now, this, like I said, is a single step of the algorithm. We take in the seed, we return the next state, but we want an infinite range of random numbers. So I could implement this using like iterators or ranges or something. I'm going to use coroutines. So a coroutine is like a generalization of a subroutine or a regular function. A subroutine will enter here up the top. It will exit at a return statement or when control flow goes off the end, and that's it. A coroutine, however, you can pause or suspend and then resume execution later. And one way we can do that is using the keyword co-yield. Now, co-yield doesn't have a built-in meaning it's actually customizable, and that's customized using the return type of the function. And the kind of behavior we want here is kind of similar to like a Python generator, right? We want co-yield to send a value back to the caller and suspend, and then be resumed when another value is asked for. Now, there's no generator type in the standard library for C++20. There should be in C++23. So we're going to have to use an open source implementation. Fortunately, I do have one that I wrote myself called TLGenerator, Generator. But like you can see, I don't have it installed right now. So we're going to have to get this somehow. I have Vcpkg installed on this system already, so I'm going to use Vcpkg. I could install this just with Vcpkg install TLGenerator from the command line, but I want to show you manifest files. So a manifest file for Vcpkg it's kind of like cargo for Rust or npm for JavaScript, where you describe what your dependencies are declaratively, and then the tool goes off and downloads them and installs them and makes them available and all that stuff. So we're going to call this XORShift. This is describing our program. Version string, just go 1.0.0. You could specifically say version semver here. There's a few other options. I'm just going to say that version string for now. And then dependencies. So the list of dependencies, we could give versions here. We could give minimum versions. Again, a bunch of versioning options. But for now, we're just going to say TLGenerator. And there is a package or port for TLGenerator in Vcpkg, so it knows how to install it. And we're going to save this in the root directory of our project and call it vcpkg.json. Okay. One last thing we need to do before this will work is go to our properties, go to Vcpkg, and then use Vcpkg manifest. Switch that to yes. There we go. And now when we build, then it should get our dependencies. So before it looks for the Vcpkg, it did pick out the manifest file, but before that, note that it scanned sources for module dependencies. So we're using MS-build right now, like I said. MS-build understands modules, so it's going to look at our source files and analyze them for dependencies between these files, so it works out what order it needs to build these modules in. This will be coming for CMake. Right now, you would have to specify the build order yourself and things like that. It's not very fun, but for MS-build, it does it all automatically. We are working hard on the CMake support, so that will be coming soon, hopefully. So after it scanned the sources, it installed our Vcpkg dependencies. Note that it installed them into a local directory, not some global place, so it's not going to affect any other projects we have. And it installed TLGenerator, installed a couple of transitive dependencies, which that package has, and it even used some cached binary packages because I've already installed these things before, so that's kind of handy. Even told us if we were using CMake, then we could just copy paste these into our CMake lists, but we don't have to do that for now. And then we got a bunch of build errors because we haven't finished quite yet. But that's enough for us to go up here and do #include TL. There we go. IntelliSense found the headers. So if we do TL/, there we go, TLGenerator. And then TLGenerator should light up. There we go. It found the class. And that's everything we should need. So then if we go back here and do an import, then it should, there we go, find the XORShift module. And it gives a completion for that. And we can save. I'm also going to #include TLGenerator here. There we go, IntelliSense kicked in. So now if we control click, we can navigate to the module. The normal kind of navigation things that you use should all just work fine. Okay, so that should be all we need to build and run. So again, it scanned the sources for module dependencies, it recognized that we had to build the module first, and we got a single random number out. Like I said, I want this to be infinite. So we're going to make this into an infinite loop. And that's the only change we should have to make. When we get to this co-yield statement, the coroutine will suspend. When we ask for another value, it will be resumed, and it will just keep going around this loop. So now if we run again, then it will recompile, and we get a ton of random numbers forever and ever and ever. But say we don't want just any old random numbers. Maybe we want random numbers from like 0 to 100. One way we could do that is using ranges. So ranges are a new feature in C++20, which allow you to transform or process or generally manipulate ranges of values. And one way we can use them is this pipe syntax. So we take our values, our infinite range, and we pipe them into something else, kind of like a Unix pipe, like in Bash or something like that. So we can do std views, : and we immediately get a list of all of the range adapters in the standard library. If you ever used range v3, which is what ranges are kind of based on, if you used range v3 in older versions of Visual Studio, then you might have noticed that IntelliSense really, really struggled. It was really, really hard on the compiler and on the IDE. We've done a lot of work on this, even though it was pretty much instantaneous. So we're going to transform. Transform takes some function. We're going to take each value, and we're just going to return I mod 100. And that will reduce the range from the width of a 64-bit integer down to 0 to 100. This error is just an EDG bug right now. They're going to be fixing it. Don't worry about it. Okay, so if we run this, then we should, there we go. Bunch of numbers from 0 to 100. Now this is a long-running application, right? This is just going to keep going. If you do have an application like this, or something interactive, like a video game, then maybe something you want to do is make a change in your code and immediately see how that affects your program without having to do a full rebuild or anything like that. So one thing we have for that now is hot reload. So let's say I change that, I save, it immediately recompiles, and now we have that bigger range because I have this set to hot reload on file save. So every time I save this file, let's reduce this back down to 10, save, and there we go. We immediately see the difference in our application. Some more things we could do with ranges here, like maybe we don't want this to be an infinite range. Maybe we want to, say, take the first 5 values. This is something we can do with ranges, just build up a pipeline of operations. And now this should just print out the first 5 values. There we go. And exit. Great. We could even in here, if you're not a fan of IO streams, we could hash include format. The standard library version of format doesn't come with the outputting, but if we wanted to, say, std format I new line number is, we could do something like this. Std format will do kind of Python style formatting. So if we rebuild this, there we go. We can do some nicer string formatting without having to use the carets and everything like that. And the last thing I want to show you is coroutine debugging. So like I said, this is a coroutine. There's a lot of compiler magic going on behind the scenes here. Like this function gets kind of split up a bit. It gets turned into a state machine. But the debugging experience is pretty much what you would expect. Like we can set a breakpoint, we can continue, we can even step over here. So this is co-yielding. So this is suspending the coroutine, going back to the caller, and then might get resumed later. And it just acts as if it was a regular function. So it hides all of that, that complexity from you. We even have a visualization for the coroutine frame. So if you're writing your own coroutines, trying to debug them, then you can get all the information here. The call stack, the coroutine implementation is all hidden in this external code, so it looks pretty much like you would expect. We've just tried to make the experience as you might hope it would be, just trying to hide all of the complexity which coroutines bring with them and give you a nice debugging experience. So that's our first demo. If you'd like to see more of C++20 in action, you can check out these other talks that we have at the conference. Some have been already, some are coming up. So we have things on Chrono, on documentation, in modern C++, in modules, STD format, and also in-memory and persistent representations of C++. So please do check those out. Moving on. We talked a little bit earlier about C++20 conformance. We are also starting to work on C++23 already. So we have some features which are already done. They've actually been contributed by all of you folks to our open source standard library. So thank you very much to everyone who contributed there. Coming next, we are working on standard library modules and coroutines, both the proposals for the standards and the implementations in our tools. Next up, we're going to talk a bit about code safety. There are two main facets to this, both static analysis at compile time or at design time, and dynamic analysis while your code is running. So on the static analysis front, we've been improving the checkers in our code analysis framework. We've got a bunch of new things which are available now. We also have two talks on these, one which was yesterday, one which is tomorrow by Gabor and Sunny. So please check those out. For dynamic analysis, we talked a lot about AddressSanitizer for Windows last year. It's now generally available. So we have x86 support, x64 support, support for debug configurations, and also if you want to do this on the command line or through CMake or something, you can just pass fsanitize equals address. You don't need to pass the runtime libraries anymore. And then we also have Visual Studio integration for MS Build, CMake, and the debugger. So you can see here, you get a little thing in the debugger when you get an AddressSanitizer issue. And you can check out aka.ms/asan to learn more. Also, for dynamic analysis, we now have experimental libfuzzer support. So this is an LLVM project for an in-process coverage-guided evolutionary fuzzing engine. So if you have an interface you'd like to improve the security and correctness of by just throwing as much input at it as you possibly can, then you can give libfuzzer a go. And you can check out aka.ms/cpp/libfuzzer for more details. So just to kind of cover these, summarize these, we have static analysis at different levels of depth, up from code linters running really quickly down to slightly more complex code analysis. And then we have dynamic analysis while your program's running for AddressSanitizer and fuzzing. And we're going to continue working on new approaches to these in our tools. Moving on from code analysis, we're going to talk about cross-platform, and we'll start off with Vcpkg. So Vcpkg, you kind of saw it in action a little bit earlier. It's an open source library manager for Windows, Linux, and macOS. It's a cross-platform dependency management system. We have about more than 1,700 libraries available now. And you can also add your own libraries and contribute them upstream, or just have them locally for your project. This year, we do have our own website for Vcpkg, which is at vcpkg.io. And last year, we talked a lot about some advanced features of Vcpkg, like registries, to have your own catalogs of ports, manifests for expressing your dependencies, which you just saw in the demo, versioning for choosing which specific versions or minimum versions you want, and caching, which we saw a tiny bit earlier and we're going to see more later. These are now enterprise ready. Please do try them out. They're out of experimental, and you can check out aka.ms/vcpkg/team for more details. And now I'm going to show you another demo of various features of Visual Studio and beyond. Okay, so I've taken the project which we've developed in the first demo and I've made it into a CMake project. It's pretty much the same and the experience is mostly the same. Like here's the CMake log I just generated. It ran Vcpkg, it installed my dependencies, it extracted everything we needed so that now we have IntelliSense, just like we did for MS Build. The only real difference is that I changed it to not use modules, to just use regular header files. Now, I'll show you the CMake lists. So I wanted to make this, it's not quite how you should do this. You should also keep track of the version of the library and things like that. But I wanted to make the correct install targets that you might need for a CMake library so that we could install this XORShift library using Vcpkg and then other projects could use it. So I've done a find package on our TL generator dependency. I've created a new XORShift library, which is header only right now. So I'm using interface. We could add implementations later or whatever, or just keep it as a header only library. We have that link library against TL generator. Link libraries, it's because TL generator is header only as well, but this is how you do it in CMake. And then we have our target include directories, which if we're installing is going to be in the include directory. And if we're building, then it's the local include. Then we have our sample program, which is the thing that we wrote earlier, which just has a single file. And we're going to compile with std C++ latest for MSVC and otherwise just C++20. Then we link that against XORShift. Okay, so then we want to install this library. So the first thing is we install the public headers into this directory, which is given by this little helper. Then we're going to install our targets. If we had any like runtime or library components, they would get installed into the relevant places. This is header only, so it doesn't have any, but I just wanted to include it just in case. And it's going to keep track of any targets, i.e. this add library, so that other libraries can then, or other CMake projects can use these targets. Then we take those exports and we save them into a file, XORShift targets.cmake, and we give them a namespace so that they don't collide with things, and save it in here. Then finally, we install this XORShift config file. This is what CMake will look for if you do find package. So if you do find package XORShift, then it's going to look for XORShift config. And I've made a simple version which just finds the TL generator dependency and then includes those saved targets. So now someone could find package XORShift and target link library CppCon XORShift, and it would all work. Now, this is currently targeting my local machine. You notice if I click here, it actually gives me a couple of options for WSL. I didn't add these. Visual Studio just found them automatically because I'm now using, instead of the CMake settings.json, the old format for specifying CMake configurations, I'm now using CMakePresets.json. If you want to do that, you go to Tools, Options, Environment, CMake, General, prefer using CMake presets. Then, if you go to Project, Edit, CMake presets, then it will give you this automatically generated CMake presets file. And this can be used for not just Visual Studio or Visual Studio Code, anything which uses CMake and has support for this. CMake has built-in support for this as well, so you can specify like minus preset, and it will use like these cache variables, for instance. I mostly didn't have to change this at all. The only changes I made were I got it to use my this version of GCC, which I built from source, just because it's the latest and greatest GCC version. And I added this toolchain file so that Vcpkg works, and it finds the Vcpkg manifest. Notice it comes with a version for Linux and one for Windows. It also comes with one for macOS, but I deleted that just because I don't need it. And I added the toolchain file here as well. Notice since I'm targeting Windows, I only have the Windows default option that's controlled by this automatically generated thing here, host OS, Linux, host OS, Windows. So now if I want to target Linux instead, I can just flip to Debian. And this will, there we go, switch configuration to Linux default. And then I can generate, and it's going to copy the files to the remote machine and generate everything that we need. Okay, CMake generation finished. So we can build. There we go, it built and linked, and we'll give you the same kind of browsing experience that you would expect. Just to show you, we still have IntelliSense, even though we're now developing on Linux. Okay, so I'm now going to show you how to use GitHub Actions for adding CI support to our project. So I've actually already added this .github workflows main.yaml file. If you go onto GitHub and go to GitHub Actions, you can get a bunch of templates for this kind of stuff, but I got all of this working already, so just to show you where I ended up. So it's just called CI. It will run every time you push to this branch or make a pull request. You can also run it manually. There'll be a little button if you add this workflow dispatch. And it's going to run on Visual Studio 2022. I got a couple of environment variables to tell it where Vcpkg is going to live and what the build type is. Then I check out our repository. I then check out Vcpkg in this directory. Then I have a couple of helpers to set up Ninja, to set up, to run vcvars all to get the right version of the toolchain. Then I set up Vcpkg, run CMake to configure. No, I'm using the CMakePresets.json thing here, the same thing that we had Windows default, but the same thing, and then build. So this should all succeed as long as all of these steps succeed. So if I go and create a Git repository in my personal account called CppCon CMake, I can create and push. So this has created a new Git repo. It's going to push all those changes, made a little commit. It's giving me a little status over here. And task completed successfully. So if I now go to my GitHub account, there we go, CppCon CMake, and it's got all of our project files. And now if I go to Actions, you can see it's already found that file. If it's in .github/workflows, it's a YAML file, then it's going to be found, and it's going to run our job. So you can see it running right now. It checked out our repo, that's checking out Vcpkg, it set up Ninja, it's setting up, it ran vcvars all, it is now doing Vcpkg stuff, ran Vcpkg install. So actually it set up Vcpkg already, we kind of missed that, it was too fast. So it's now going to install our dependencies. Here we go. Downloading 7-zip because that wasn't there. And it's now going to, there we go, finish configuring the CMake, Vcpkg. It then configured CMake for everything else, and now it's building. There we go. We built sample.exe. And we could run it or run some tests or do anything else we wanted. But as soon as this is finished, in a couple seconds, we should get a nice, there we go, green check mark. Okay, so our dependencies right now are pretty simple. Like this took a few seconds to get this package, and there we go, total elapsed time 9 seconds. So not a whole lot of time, but imagine we're like building the entirety of Boost or something like that. We don't want to do that on every commit if it's not going to change. So what we could do is use Vcpkg's binary caching support. So this is a newer feature of Vcpkg, which allows you to cache the binaries somewhere else so that you don't have to rebuild them every time. And it supports a bunch of different targets like GitHub packages, Azure DevOps, blob storage, cloud storage, some folder on a server which you own, whatever. And it also has some instructions here for using GitHub packages, which I can use right now. So the things I need are, I need these binary sources list. So this just says to use NuGet and GitHub. So I can go back here, put this here. And then the only other thing I need is this. It assumes that Vcpkg is being bootstrapped, which we do right here. So I can just paste this here, get it all nicely lined up. There we go. Replace owner. We can do here, Tartan Llama, and here. And that should be all we need. We don't need this matrix.mono. This is, in these instructions, it's using both Windows and Ubuntu. I'm just using Windows for this example, so I don't need that. And now, if I add this, add binary caching, commit it, and push, then there we go, that pushed. So now if we go to our GitHub Actions, there we go, add binary caching. You can see I tested it a little bit earlier, but this is now going to do the same process that we just had. The only difference is instead of just checking out the everything in when it runs a Vcpkg install, instead of just pulling down everything from source and building, it's first going to check where if we have built packages already cached that we can then just download. So we should see that once CMake configures. Here we go, running Vcpkg install. So when this tries to get our dependencies, we should see it looking for cached binaries. Now it won't find any yet because we haven't installed them, but there we go. Attempting to fetch 2 packages from NuGet, and it didn't find any. Restored 0 packages because there aren't any yet, but once it did install these dependencies, it then uploaded them to the NuGet source, which is my GitHub packages. So once all of this finishes and GitHub's caches get a chance to update, then in my Tartan Llama packages, this will very shortly be populated with my 2 packages. In fact, I can just skip. There we go. That took about a minute. So these packages are now available, and it had some information about how they were built and everything like that. So now if we go back here and rerun our job, then instead of it building these from source or having to do any additional work, then it's going to just pull down the binaries immediately. And I'll just again skip. Okay, so we're now running the Vcpkg install. So very shortly, there we go, attempting to fetch 2 packages from NuGet and restored 2 packages. Didn't have to do any additional work. So if you're going to be building heavy dependencies from source, you can use binary caching to save yourself a lot of time. All right, I've got just a couple more things I want to show you. One is AddressSanitizer. Now, we showed AddressSanitizer in experimental mode last year, but it's now out of experimental and ready to use. So let's say that instead of using random numbers, I have a std vector of std uint 64t called vec, and I do std ranges copy from random numbers to std back inserter. Oops. Of vec. Just copy all the numbers over into vec, and then do a regular for loop and have an off by 1 error. I is less than or equal to vec.size rather than less than, and plus I, and then index vec here. This is an off by 1 error. This is undefined behavior. I'm reading past the end of this vector. So now I could let this just crash horribly. What I'm going to do is enable AddressSanitizer, which I do by passing the fsanitize address flag in here, generating CMake. Skip to when this is done. Okay, we're done. Now we can go to our sample. We can build and run. And what we should get is a report from AddressSanitizer telling us that there was something wrong. So here's our console, which is where the report should go. And we should also get a break point at the place where the failure happened. Oh, you saw that. There we go. Error from AddressSanitizer, heap, buffer, overflow. And it tells us what the bytes are in the buggy address were, everything like that. And it also tells us where it occurred. And note that we didn't have to specify the runtime libraries or anything like that. The compiler driver worked it all out. Okay, one last thing to show you, and apologies for the different sound, my good microphone just died. I want to show you creating a Vcpkg port for the program we have just created. So we have two files, vcpkg.json and portfile.cmake, and these are both in the vcpkg/ports/xorshift directory. Now, the vcpkg.json file is going to be the same as this one. The only difference is we also want an additional dependency on vcpkg CMake, which is a little helper project to give you some additional tools for telling vcpkg how to build and install your program. And we'll set the host equals true option just to say we only need this for building. Then we have our port file. So the documentation for this is all online. You can find a bunch of examples. I already know how to do this for my project, so we're going to check it out from GitHub. We're going to store the source path in this variable, source path. Our repository is tartan llama /CppCon CMake. Our reference is some head commit, essentially, or a release tag. I'm just going to use the commit ID. And then we need the SHA-5112, which I don't know yet, but Vcpkg will tell me. Then we run a configure using the source path, which we saved earlier, this thing. Then we run vcpkg CMake install. Then we just need to vcpkg clean up a little bit. Vcpkg is going to install 2 copies of these headers, one for the debug build and one for the release build, but we don't need the debug one, it's just going to be the same. Then we install a license file from source path /copying. My license just says do whatever you like. And we're going to store that into destination, current packages directory /share/xorshift. And we're going to rename it to copyright. This is just something which Vcpkg expects to be there. Now we can run vcpkg.exe, install xorshift, and install it for x64 Windows. there we go, it's going to install our TL generator dependency. I must already have the Vcpkg CMake dependency installed. And it failed because we got hash mismatch. I can just copy paste this in, rerun, and hopefully this passes. There we go, installed, and it tells us how to use our package. Remember, we gave it this this namespace, so it all worked.
So as you've seen from side demo, CMake is a first-class citizen of Visual Studio, and we're constantly improving the experience based on your feedback. So please keep that feedback coming. We're also very excited about the recent collaboration with Kitware on supporting CMake presets, both inside Visual Studio and Visual Studio Code, and natively in CMake, which opens the door for a seamless on-ramp for your project, for your CMake projects built by your team with either VS or VS Code into CI systems. And if your code base targets Linux, let's talk about the debugger. Again, now you can also use both GDB and LLDB to attach to remote Linux or Unix processes. And you can also debug Linux core dumps in WSL with Visual Studio. There's a lot more than meets the eye with Visual Studio support in Linux. And to give you a glimpse of that, allow me to show you a short video clip here from the makers of Diablo 4 from Blizzard.
We at Blizzard develop our servers on Windows, but we actually build and deploy them on Linux. When we experience a crash in our environment, we like to grab the core dump and figure out what went wrong. We on the online team, we're pretty used to looking at crashes on Linux. The game programmers actually write game code that's deployed on Linux, but they're not as familiar with debugging on Linux. We had always wished we could use Visual Studio to look at our Linux crashes. I saw a couple of blog posts written by Erica. I reached out to her with just kind of a blind email, I think, and said, hey, I'm trying to do this thing, and can you help us? The actual goal was to be able to use Visual Studio, which is the tool set we're all familiar with and we love. The idea of doing that has always been unattainable. We started having a discussion about what problem we were trying to solve. And pretty quickly, she involved some developers. We validated that eventually, yes, this is doable. A couple of months later, a preview version of Visual Studio came out that had this feature in it, and we tried it and it worked.
So what Visual Studio does is it enables C++ developers to remote debug Linux cores on WSL or a remote Linux system using the front end of the Visual Studio debugger. Visual Studio doesn't care how you compile your Linux binary, so you can be using a build system like Make, CMake, a custom build script. The only pieces of information that you need to provide to Visual Studio is the Linux path to the core, the Linux path to the binary that produced that core file. Debugging Linux cores or crashes on Linux servers is not restricted to just a few Linux devs who are comfortable using GDB from the command line. It democratizes that whole process. We were able to develop a solution, validate the solution with Blizzard before we built it, and then make sure that it addresses the underlying problems and also the problems faced by the rest of the C++ cross-platform community.
When you parse this in Visual Studio, the tools available to you are so much better. We use the parallel stacks tool. It shows you your entire process space, like from a 30,000-foot view. And it lets us home in on the problem just so much faster. It's incredible. And how responsive Microsoft was. That was just a fantastic experience.
All right, I hope you found this intriguing. And if it's not you that it's working on Linux program, you may know a friend that does. So be a good friend and share this link with them. And now let's talk about productivity. What can we expect from Visual Studio 2022? From the IDE moving to 64-bit, which will allow VS to tend to the needs of more complex and the largest code bases out there to new ways on how you can use colors and the streamlined Git experience you saw in Sai's demo. There's a lot to be excited about Visual Studio 2022. And let's talk about the debugger again. You've seen hard reload in Sai's demo, but that's not all. Dependent breakpoints and force run to cursor are just a few of the enhancements coming to Visual Studio Debugger in Visual Studio 2022. But now that what I do want to spend more time on today are the performance improvements we've been making in the past year. And when it comes to performance, we did a 360 on the full inner loop, basically looked at each stage, edit, build, debug, and identified the areas that would bring the most significant improvement to your day-to-day work. So let's start with the editing experience, where finding files, operations now will be 1.8x faster. This particular measurement is on a Chromium code base. Opening files in the editor will feel more instantaneous now, with a significant reduction in the time it takes until you can actually start typing in the editor. This particular measurements are done on Unreal Engine 4 code base. Something that happens immediately after the file is open and rendered in the editor is the background IntelliSense parse that kicks in. This is what renders the semantic colorization in your editor, as well as make IntelliSense operations like member list work. The time it takes, of course, depends on your translation unit size, which is the size of your file plus all the include headers. But in our measurements, we've seen that the new VS version performs approximately twice as fast as before. The goal is for Visual Studio to just feel lighter, more responsive. And we want that, also want smaller operations that we do 1,000 times an hour to feel faster. One example being member list, which usually shows up under 200 milliseconds. And Visual Studio 2022, member list will pop up even faster. We've also partnered with the amazing Epic engineers to investigate improvements we can make specifically for folks using Unreal Engine to develop their games. And I'm thrilled to report that starting with version 4.27.1, Unreal Engine will come with changes in their VS project generation that will enable Visual Studio to provide IntelliSense when you open a file in the editor 18 times faster. Oh, and this UI version is out now, so you can go and check it out. And you can learn more at the AK link below. You know, the faster Visual Studio gets out of the way, the better and more productive you're going to be. So with this latest improvements, we want Visual Studio 2022 to be the most productive C++ environment out there. But that's not all. Last year, when we came here at CppCon, we shared improvements in linker time. There were 2x improvements compared with previous versions of Visual Studio. But that was just the beginning. Even before CppCon, we were already working, CppCon last year, we were already working on some sweeping changes in our old linker code base. And as this saw the light of day, we worked with the coalition, the makers of Gear 5, to measure these results. And for this code base, we measured an impressive 28x improvement in link time. When we work with Playground Games and Turn 10 Studios to measure the link time for Forza Horizon and Forza Motorsports, we saw similar large speedups. This is linking is a fundamental step in your day-to-day inner loop. So we hope you'll find this improvements really useful as well. And let's talk again about the Visual Studio Debugger. With this huge linker improvements, now you can easily move your code bases to use the /debug full as a linker switch, which will yield additional benefits in your debugging experience as well. But that's not all. When it comes to debugging, we also did substantial improvements in the runtime performance of the default Visual Studio debug configuration. There are many benefits to use the debug configuration, whether it's the runtime checks, the additional debugger features like just my code stepping and hot reload. But sometimes this functionality adds enough overhead to your time-sensitive code that pushes it over a threshold where you have to switch to an optimized build to see your app functioning normally. We hope that with the recent runtime performance work in both Visual Studio 2019 and in 2022, that improves the debug configuration runtime performance by a factor of 2 or 3x. It's enough of a threshold that will allow many of you to reconsider using the default debug configuration and benefit from the fantastic debugger features that Visual Studio Debugger has. And if these improvements turn out to not be sufficient for you, do please reach out to us. We know this is an iterative process, and we want to make Visual Studio give you the knobs to get the best of both worlds, a fast app and the best debugger features for it. This slide hopefully paints a picture of how the latest Visual Studio brings you the most compelling C++ experience yet in terms of performance. This wouldn't be possible without the hard work and patience of so many of our customers that report issues, that help us investigate and validate our changes before we make them available to all of you. So big thank to everyone involved, especially to the 4 game studios, Blizzard, Turn 10, Playground Games, and the Coalition, who are open to work closely with us. And expanding on that, improving Visual Studio would not be possible without your voice, whether it's performance that's top of mind for you, or maybe correctness, whether you have a suggestion or maybe you want to report a bug, head over to our developer community portal. The link is down there below, and help us build a better product for your particular code base. Because as I mentioned at the beginning, we are listening, and it is our mission to empower you and every C++ developer and their teams to achieve more. So on behalf of the whole C++ team, Sai and I want to thank you for tuning in, and we want to wish you happy coding.
Yeah, and if you have any more questions, feel free to join in the GatherTown Q&A, or hit us up on Twitter at mluparu or at tartanlama. Or you can join the Visual Studio channel on the CppCon Discord. And please do remember to take our survey. It helps us a lot. And also check out our other sessions that we have going on for the rest of the week, and have a great conference. Thank you very much.